This video is going to be a video on position versus time graphs, sometimes known as displacement versus time graphs, and occasionally distance versus time graphs. But by and large, they should just be known as a position versus time graph. So I'm going to review some graphing techniques in this video on how to calculate the slope of, a graph of a linear relationship. But it shouldn't be brand new information for you for the most part, at least as far as graphing is concerned. The physics side of things gives you equations that we'll have to use further on when graphs aren't available. So typically, if we're doing this in the class, I usually get students involved and usually make them walk back and forth as an example of pointing out the differences between displacement and distance. So you'll have to bear with me in this little activity. I'll kind of somewhat recreate the same scenario on this little YouTube video. So not animated though, sorry. So suppose I get someone right here, we'll call them person X, to walk forward to the front of the room and just pick something up off my desk or maybe write something on the board. So if that's the case, they get up and happily walk to the front of the room and they end up moving 6 meters north. So they have a displacement of 6 meters to the north of their actual desk to their final position, which is the front of the room. In this case, they also traveled a distance of 6 meters. The difference between distance and displacement. Displacement, of course, uses direction. So person X walk forward 6 meters. So walk 6 meters north. So if we actually time this, and I'm going to pick some random times here, or simple times for the most part, and say that, okay, when person X was at their desk, we'll call that position 0, and we're going to call that time 0. As they walk towards the front of the room, we'll just assume that for every meter they walked forward, it took them 1 second, and just have a nice, simple relationship. So from roughly this desk in my class to roughly where my desk is about 6 meters. So these are some times that would be associated if they're walking at a pretty steady pace. What do we do when we get an actual chart? We, of course, go and plot it. So I've got a little graph right here. It's just a small little thing. It's not going to be the full page. It's just tiny because it's going to be nice and quick. So whenever you have information like this, you have yourself a position time information. So time is typically going to be the X variable. So that's going to be the time axis. So of course, we can look at the title of this graph. It's called position versus time. So sometimes you'll see it written down as just D versus T, and that's fine too. Sometimes written out position versus time. Sometimes you'll just see the units next to it as well in the title, but at the very least, the title should tell you which one is the x-axis, which one is the y-axis, and that's all done for us in this little chart right here. Time is the x-axis, position is the y-axis, and we have positive here, and now that implies that we are going north because north is going to be the positive direction. So if we put all this data on the actual graph, it kind of looked like this. At point zeros, we were at 0. So at 1 in the time graph, we are at 1 on the position axis, 2 and 2, 3 and 3, 4 and 4. There you go. So this is a nice linear relationship. So when we draw a line of best fit, it should just go through all the points and you have a nice graph. So anytime you have a linear relationship, you technically have a constant slope, which therefore means we should find the rise over run. So your slope, again, is your change in your y divided by your change in the x. That's why it's called rise divided by run. And hopefully in math class, and at least in a previous video, I at least walked you through that you find the difference between 2 points in the y-axis and you find the difference between 2 points in the x-axis, and you generally want these two differences to be as far apart as possible. Now, if I tie this into physics, this is not technically an XY graph. This is a position versus time graph. So technically the y-axis has a change in position, which is known as a displacement. The x-axis, of course, is a change in time. So instead of having y's and x's, we're going to use a bunch of d's to represent position and a bunch of t's to represent time. So that's kind of the only difference between this just being a math graph versus a physics graph. In a physics graph, we actually have to change our variables to accurately describe what's going on. Computationally, it's going to be the exact same as what you would have done in a math class. You just, now instead of at y2 minus y1, it's position 2 minus position 1. Instead of at x2 being minus x1, it's going to be time 2 minus time 1. So that is really the only difference. You're still going to calculate slope the exact same way. You're just expected to use different names for your variables now that it's a position time graph. So that's probably one of the hardest things to get across at the grade 10 level is you're technically still doing this math that they taught you in a math class, but you're going to call them different variables. And sometimes it's going to be a v divided by a t, sometimes it's a divided by a t, sometimes it's an f divided by a t, but most of the time it's going to be time in the denominator. So pick your 2 points. So again, if this was a math class, you'd have your point 2, which is the furthest to the right. So that's x2 minus x, or x2 and y2. And the point I'm going to pick on the furthest on the left, that's going to be point 1. So x1, y1. And of course, I'm going to pick the origin because that's a nice, easy one to pick. So recognize that now, instead of it calling your point x2 and point y2, it's going to be time 2 and position 2. Over here, right, the origin, it's not x1 and y1, it is time 1 and position 1. So just a little bit of the language and symbol changes, but again, mathematically, it's identical to what you do in a math class. So you pick your 2 points. So over here, it's 6 in the time axis, right, all the way down there to 6 in the position axis, and of course, the origin's pretty straightforward, 0 and 0. And then you input those numbers into your actual equation. So position 2, again, is the one furthest to the right. So I put that in there on my equation. And then, of course, you subtract by 0 meters. So that's position 1. And then we have time 2 should be 6 seconds. And, of course, time 1 is 0 seconds. So it's always position 2 minus position 1. So you do your math computation. 6 minus 0 on the top and the bottom ends up being 6 divided by 6. So that gave you a slope of 1 meter per second. So we have a rise of 1 for every run of 1. So that's all that is getting at. Now, this ended up being a positive number. And since we've got an actual direction, we know positive is north, then we can actually associate that with the direction. So because we calculated a positive 1, I could call this 1 meter per second north, which means the person who is walking towards my desk in the classroom would be traveling north with a speed of 1 meter per second. So because there is a north, it is therefore a vector. Even just recognizing that it's a positive value is also enough to indicate that it is a vector. So then typically this slide comes next. So because we have a speed with a direction, it is known as a velocity. So that is really the only difference between a speed and a velocity. Whereas speed would just not care about the actual direction. Velocity has both magnitude, so that's the numerical value, 1, and it has direction. So that's where you either can write it down as a north, south, east, or west, or just a simple positive or negative would usually be enough. If you are going to write it down as a positive, a lot of times students just write it down as 1 meter per second and still say it is a velocity, and they're not overly wrong because it's not too often you'll actually write down the physical positive value. That's usually how they just leave that part out typically. And therefore it becomes kind of hard to tell the difference between whether or not you have a velocity versus a speed. Because again, speed has a pretty close to the same equation, your distance divided by your time versus your displacement divided by your time. So you just have to keep in mind that a velocity involves direction. So since we calculated the velocity over the entire interval, we've technically calculated the average velocity. Now for the graph that we have, the average velocity would have been the exact same as just the velocity. It still would have been 1 meter per second going north. Sometimes if your graph starts having ups and downs, the average velocity would definitely be different than the actual velocity at any given point in time. So average velocity is very similar to your average speed equation, which you saw in a previous video. That's just your total distance divided by your total time. Your average velocity is your overall displacement divided by your total time. Or it could just be the displacement between 2 points on a graph divided by the time interval in between them. And I'll give you an example of those in the next little graph. So usually in class, I'll pick on whoever's on the left side of the room now, or the west side of the room. I'll say, okay, person X over here. Probably should have called that person Y, but person X over on the west side of the room, I'd say, okay, same thing, come to the front of the room and maybe do a math problem on the board. And so then person X would kind of walk forward, and then usually at this point, they often forget, or even might just say, never mind, I'll do it myself. And the student will go, oh, okay, whatever. So suppose they traveled 4 meters north, and I said, nope, never mind, go back to your desk. And then they go, okay, fine, they'll go backwards. And they go backwards 4 meters south, and they're back at their desk. I said, oh, I've changed my mind again. Maybe come to the class in front of the room and do this actual math problem for me. So after a moment or two, they get a little frustrated, and obviously because I've changed my mind a couple of times, and because they're a good sport, they'll typically walk to the front of the room, do whatever math problem I asked them to do, and then everyone's happy. At the end of the day, person X on the west side of the room still traveled 6 meters north because they went from this position to the front of the room. Albeit that person walked forwards and forwards again. And so if you combine them together, 4 meters forwards, then I said go back. So you add that backwards, 4 meters backwards, and then add that overall 6 meters forwards again. This person traveled a total distance of 14 meters. All right, but their overall displacement is just 6 meters because if we consider where this person started from versus where they ended up, that's still just 6 meters north. So that is kind of the big difference between distance versus displacement. Now, next we'd typically graph this thing to kind of give you an idea of what's going on. Now I'm just making up times here for the purpose of just having a graph. So let's just suppose that first time they walked forward 4 meters, it took 2 seconds. And I said, nope, change my mind. The student walks back a lot quicker because hooray, relief, they don't have to come to the front of the room. Let's pretend that took 1 second. And then they maybe sat there and mulled for about, 4 seconds. Well, I said, no, change my mind, come forward. And they got a little annoyed, obviously. And then they came to the front of the room and that took them, let's just say 2 seconds. So those are just some made up times just to help move this scenario along. So again, up on the graph is still positive north. So that's what we're going to work with. So this is a slightly different graph, a little bit more involved than the previous graph, but we'll analyze this as well. So what we're going to do is we're going to find the slopes of each of these sections. Now the slope of a position time graph is the velocity. So if I say calculate the velocity of this person's trip, you'd actually have to find the velocity for this blue line, the red line, the orange line, and the green line. And so that's what the rest of this video is going to be about. So if we look at the velocity once again is your slope, which is your rise over the run or your change in your position divided by your change in time. So our change in our position for the first one, so d2 minus d1 all divided by t2 minus t1. Remember, that's the same idea as y2 minus y1 divided by x2 minus x1. We just now have a position versus time graph. So once again, that should be the same as a math class. So picking 2 points, I usually pick the end points whenever possible. If that's not possible, then obviously pick a different point between, but this one was purposely drawn to be nice and simple. So this point right here is going to be my point 2 because point 2 is always furthest to the right. And so there's my time value, 2 seconds. If you go down here, yep, 2 seconds. I can't draw with the mouse. So 2 seconds down, and then of course 4 meters up. So there's my y value, and there's my x value technically. And I'm going to pick the other value to be the origin, which is just 0, 0. Plug that into your actual equation, d2 minus d1, or looks like that. So this should be nice and simple. 4 divided by 2, because we can just more or less ignore those zeros. So 4 divided by 2 is going to give us 2 meters per second. So again, the units here have to stick around. They're not going anywhere. So, and because we got a positive value, that implies that we are, of course, moving north. So I'm just going to leave it as a positive 2 rather than call it 2 meters per second north. So moving forward. Next, this red slope right here, same idea. We'll call it V2 for slope number 2, or in this case, it's going to be velocity number 2. And because velocity is a vector, we have to remember to have these little arrows above it. So we'll do the exact same thing. We need 2 points. It's our change in position divided by our change in time. So we'll pick in our 2 points. And I'm going to pick again the 2 endpoints. So point 2 over here is going to be at 3 seconds. We are on the time axis. So that means our position, if we go over here and look, our position has to be 0. And then our point 1, so this guy right here, that's the same point as the last one. So it's 2 seconds in the time axis and 4 meters on the y-axis or the position axis. So plug all this stuff into your actual equation. And so it ends up with being 0 meters minus 4 meters all divided by 3 seconds minus 2 seconds. So that's math that you can pretty much do in your head. You end up with negative 4 meters divided by 1 second, which means you have a slope of negative 4 meters per second. So this now negative means we are going backwards. Or I could have written this down as 4 meters per second. And since it's going in the negative direction, I could call it south. So that is still a good indication that we're dealing with vectors. So in the first 2 seconds, this person walked north at a rate of 2 meters per second. In the next 1 second, the person walked south at a rate of 4 meters per second. So doubled his or her speed. So there's your 2 slopes. If it's a positive slope, generally you can take that as moving forward. If it's a negative slope, you can generally take that as moving backwards. So since forward and backwards has been defined as north versus south, you can just call it north up here if you want and south down here. So the next slope, slope 3, you'll notice it's just a flat horizontal line. It's on the time axis, but it is a horizontal line. Anytime you have a horizontal line, your overall change in your position is 0, right? It's not going up, it's not going down. So your rise on your graph is 0. And when there's no change in your vertical position, there is no slope. So if it's a position time graph, a horizontal line, wherever it is, it could have been up here, right? Person could have stopped here and had a pause when they walked forward for a couple seconds. They could have just paused for a second in annoyance. So that horizontal line could have been drawn up here. It doesn't matter where the horizontal line is drawn. If there's no slope, that person is at rest. They are not moving. There is no motion. So therefore, your horizontal line here on the axis is 0 meters per second. It just happens to be on the x-axis or the time axis because they walk back to their desk. The last slope, so that's going to be this green one here when they walk to the front of the room. So same idea as the last 2. You would just find your change in your position divided by your change in time. So d2 minus d1 divided by t2 minus t1. And so picking the 2 points, again, this is 0.2 and this is 0.1. So always written down as x, y, and again, this is time, this is position, but just to be familiar with math, it's always x written first, then y. Just plug them in. So moving forward, you'd have 6 meters minus 0 meters, and you'd have 8 seconds minus 6 seconds. Do some division. So 6 meters divided by 2 seconds gives us a positive 3 meters per second. So once again, it's positive. So whoever this person is, they walked forward or they walked north in front of the class. Okay, so those are just all your slopes and how they relate to velocity, right? So the slope of a position time graph is your velocity. Please don't forget that. So the last little bit is finding the average velocity. So the average velocity, in this case, we're going to do the average velocity over the entire 8 seconds. So because it's going to be over the entire 8 seconds, I would just draw a new slope from the very beginning to the very end. So because of that, I drew it as a dotted purple line just to kind of show that this is different, right? This is not the actual path that the person took. This is just the average. The average takes into account for when they move forward, when they move backwards, when they were at rest, and when they move forward quickly. So it's going to pretty much account for all of that. And so the equation for the average looks more or less the same. The only difference is you're doing it, in this case, over the total time. I could have asked for the average velocity from 2 seconds to 8 seconds, and they would more or less look like this, if I could draw a straight line with a mouse. And if that's the case, then that would find the average velocity just between 2 seconds and 8 seconds. I'd still find the slope the exact same way that I'm about to from the beginning. So I just won't add that into the video. Okay, so picking 2 points, I'm going to pick this final point here because that's a nice easy one to work with. And I'm going to pick the origin because once again, anytime I can involve the origin, I will, especially since the data goes through the origin. So those are going to be my 2 points, which will make the math nice and easy. You basically you can ignore those because it is 0. So 6 minus 0, 8 minus 0, still 0. So you have 6 divided by 8. So mathematically, that should give you about 0.75 meters. And of course, we keep the units involved, so it's a meter per second. And it is a positive. I have a slope that is going up on my graph, so therefore it is north in direction. We are moving forward because it is a positive value. So if it went downwards, I would say that it's definitely a negative. So if I said, for instance, I'll just pick a different color here. I'll pick pink, magenta. So if I said find the average velocity from 2 seconds to 6 seconds, the average velocity graph would just be a straight down, oops, can't draw a straight line, would be a straight slope from this point to this point right here. And in that case, the average velocity between those 4 seconds would be a negative value. So it does depend on what two time intervals they're asking the average velocity from. But the average velocity won't describe every little moment in time. It'll just give you the overall idea of what happened. So I hope that was enough to get you moving. On page 18, or at least it's page 18 now, it might change depending on what I add or take away from the note package that you have. Probably won't make a new video if I do change it. So at the very least, you should find somewhere around page 18 a page that has position versus time graphs. I believe there's just 3 of them on the page, and it well, gives you graphs that are kind of similar to what I did on this video. And if it asks for all velocities, for instance, it just wants both these slopes. This would be slope 1, this would be slope 2. In other words, they would be the velocities. If it asks for the position at 4.5 seconds, I don't really want you to go here and go, oh, where's 4.5 there? And then basically just work your way across. I would like you to mathematically solve for that. As a rough idea of what that looks like, this is going to assume that you finished part A first. You'll need to do part A before you can do part B, and I'll just give you a quick little idea of what to do. You would use velocity 2. Sorry, I'm drawing this with my mouse. So you use velocity 2 and recognize that you would have this answer already. Right? This guy would be found already from part A. So if you were looking for the position at 4.5 seconds, you'd plug in your number here, and then you'd actually just do the slope again, position 2 minus position 1. Little vector arrows above. That's how I draw my vector arrows. It's a little sloppy over here. All divided by time 2 minus time 1. So here's how I do this. I'm not going to work it all the way through, but you'll get an idea. So from part A, you would have this answer, right? So you would know this if you do part A first. And part A is just find the slope. And you could just do this equation to find part A. So to find the position at 4.5 seconds, we know this is going to be our time 2. Right? So at 4.5 seconds, it's this point right here. That is going to be our position, our point 2. So that would involve whatever that position, that unknown position that we're looking for. Draw time first. So we have our time 2 to be 4.5 seconds, and we include our position 2, which is what we're looking for. All right, that'd be our position 2. So 4.5 and unknown. So this would be unknown. We need to solve for this guy. We know what T2 is, so that'd be 4.5. I'll write some of these numbers down. And then our 0.1, so that would be all the way back here at the little top there, you would actually know this point right here. This would be at the time of 4 seconds, so 4.0. I'm just going to be quicker about it because I'm drawing with the mouse. And it would be at a position of 26.0 meters. Right, so you actually know this point, right? You just don't know this D2. And so we'd actually plug it in there. We'd have our 4.0, because it is 0.0 seconds, and we'd know this guy is 26.0 meters. Right, and so you have your answer from part A written there. The only thing we don't know would be this. So it'd just be a matter of solving this equation, do a little bit of the math here, and then manipulate to solve for D2. I walked you through this point. I think you can do the rest on your own. That's probably some of the harder questions that you'll face with doing these types of graphs. So if that was helpful, great. If you have questions, feel free to send me an email. You might have down in question 2 or 3 a question where you're trying to solve for time 2. And then you'd more or less do the same thing. Just figure out everything that you know in this equation and then just solve for the thing that you don't know. And so you would just do some transposition of the formulas. Okay, I'm going to go because it's kind of got long on me. I'm very sorry. Have a good day.